A very warm welcome in the class of power series and Taylor series in Mathematics 1. Myself Rupak Bhattacharjee, Assistant Professor, Department of Mathematics, GIS College of Engineering. In this particular lecture, we are going to emphasize on mainly power series. Already in the last lecture, you got the idea of Taylor's theorem and Maclaurin's theorem and the Taylor series expansion with Cauchy's form of remainder and Lagrange's form of remainder. So already we have the concept of remainder forms, which is also one prerequisite for this discussion. Along with this, the concept of differentiation or the techniques and successive differentiation is also important over here. And the concept of MVT, and you can say that generalized MVT or nth order MVT is also a prerequisite for this particular lecture. So now let us start the discussion for today's class. First of all, we are going to define power series. What is a power series? A series, we know about the construction of series, infinite series, and so on. Now we are specifying something like that, a series of the form A0 plus A1x plus A2 x square. So I think now you are able to identify the pattern for this one. In a similar manner, suppose rth term ar x to the power r plus dot 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 means you are getting one infinite series in this form. What can be written as n starts from 0 to infinity an x to the power n. Now if you break it up, the summation sign, then you will get a0 plus a1x to the power 1 plus a2x square and so on, and it will go up to infinity. It is an infinite series. It is sometimes mentioned without writing the index n equal to 0 to infinity with only the summation sign. It is actually known as a power series in X, and obviously the numbers associated with it in the form of an are called its coefficients. Okay, so this is the general definition of the power series. Now whenever it is associated with the discussion of series, the concept of convergence will come into play, and there are various ways of defining the convergence of power series, and there are various ways of checking the convergence also of power series. But we are now taking one information like that: if for any power series summation an x to the power n, there exists a definite positive number, capital R, such that The series converges for every mod x less than r, means you are taking the value of x in such a way that you are getting the defined number as capital R, and mod of x is less than R, and simultaneously diverges for every mod of x greater than R, then this R is called very importantly the radius of convergence. Then this R is called the radius of convergence. Now this concept is going to be tested and verified by some problems also, and there are techniques through which we can find out the radius of convergence of a given or of a specific power series. Obviously there are more than one, but we are now going to use this particular form. The radius of convergence we are going to find out by this formula, that limit n tends to infinity mod of an by an plus 1. You know what is an plus 1. These are nothing but the coefficients of the power series for nth term and n plus 1th term. So all these conceptual informations will be clear if we go for the problems. So let us go for a problem, and our first problem tells us that find out the radius of convergence of the series given as 1 plus 2x plus 3x square plus 4x cube plus dot dot dot. That means the coefficients are gradually 1, 2, 3, 4 and so on. Now the definition what we have learned in the last slide, according to that, if we are trying to find out that R where limit n tends to infinity an by an plus 1. Now we can write limit n tends to infinity. Modulus is not required because all coefficients are positive over here. So an is going to have the coefficient as n plus 1, and an plus 1 is going to have the coefficients n plus 2, because a0 is 1, a1 is 2, a2 is 3, so an will be n plus 1. It is very simple. And now according to the general technique for finding out the limit when n tends to infinity, what we have to do, we have to divide it by n. So it is 1 plus 1 by n, and it will be 1 plus 2 by n. Now putting or trying to find out the limit for this expression, we are getting it 1 by 1, that is 1. So what we get, the radius of convergence for this given series is 1. That means if you are taking mod x less than r, that means if you are taking the values whose modulus is less than 1, for all those points this power series will be convergent. So here it will be for greater than minus 1 less than 1, because if we are taking any value within this particular range, we will get always their modulus will be less than 1. So similarly, we can go for another problem and we can find out the radius of convergence of this series. Suppose 1 plus x plus 2 factorial x square plus 3 factorial x cube plus dot dot dot. In a similar manner, when we are trying to find out the radius of convergence with the same formula, limit n tends to infinity, a n by a n plus 1, we will write it as limit n tends to infinity. Here our a n is n factorial and a n plus 1 is n plus 1 factorial. So in the next line we can write it as limit, after simplifying these factorial expressions, 1 by n plus 1, which is nothing but 0. So radius of convergence is 0. It means the series will converge for no value of x except x equal to 0, and if you put x equal to 0, obviously the series will become 1. A finite number will be coming, that is only 1, because all other are 0. So radius of convergence is 0 means the series is converging for no values of x. Nowhere it is convergent except the value of x equal to 0. So this is a beautiful observation regarding radius of convergence. Now we can think for the radius of convergence for one more problem, that is, suppose it is given as x plus x square by factorial 2 plus x cube by factorial 3 plus dot dot dot. So for this particular problem, if I want to find out the radius of convergence, limit n tends to infinity, a n by a n plus 1 is equal to limit, by putting the coefficients and the reciprocals, we will get it as n plus 1 factorial by n factorial, which is nothing but limit n tends to infinity, n plus 1, which tends to infinity, means the series convergence absolutely for all values of x, because we are getting the radius of convergence is infinity. That means it is, you can take any value and it will be always less than r, its modulus will be always less than r, because r is infinity now. So we will get the series will be convergent for all values of x. So this is the problems or the concepts related to radius of convergence of a power series. Okay, now we will move forward and we will try to find out the power series expansion of exponential function. So now our target is to deal the exponential function with the help of power series. Okay, so the problem will be addressed in this manner, that we are taking fx as e to the power x, and we know that if fx is e to the power x, f dash x, f double dash x, all will be e to the power x, and according to the power series expansion for f n theta x, we will get it is as e to the power theta x, because if n x will be to the power x, but we are putting theta x in place of x, we will get it is as e to the power theta x. Now the most important part, that is the remainder term. Now Rn is equal to x to the power n by n factorial fn theta x. Fn means here it is the order of the differentiation fn theta x, where 0 is less than theta less than 1. We can write it as x to the power n by n factorial fn theta x is e to the power theta x. We can write it as e to the power theta x. Now check it that since x to the power n by n factorial is equal to 0 as n tends to infinity, and e to the power theta x, this lies between e to the power 0 and e to the power x, because theta is lying between 0 to 1. So e to the power theta x will lie between e to the power 0 and e to the power x. That is, it is bounded. So you can say that, so it is bounded. That is, together with Rn will tend to 0 as n tend to infinity, because this x to the power n by n factorial part will be dominating this bounded exponential function e to the power theta x, and hence we can say that the infinite expansion for e to the power x is valid, because we are getting the remainder term is going to be 0. So using Maclaurin's series, what is actually discussed in the previous class, Maclaurin's infinite expansion, just our job is to, before applying any series, our job is to check whether the required things for using those expansion is satisfied by the given problem under given condition or not. If it is satisfied, then we can easily use those particular standard form, and what we get it here as fx is equal to f0 plus x f dash 0. Obviously we are using Maclaurin series, x square by factorial 2 f double dash 0 plus x cube by factorial 3 f triple dash 0 plus dot dot dot, and we know that we have taken here fx is e to the power x, so this can be substituted here and we can write it as e to the power x f0. We can find it out from this, because as already it is calculated over here, we can write it as f0 is equal to e to the power 0, that is 1, f dash 0 f dash x is equal to e to the power x, so f dash x means f dash 0 at x equal to 0, it will be also 1, and so on. So using these results here, we can write it as 1 plus x plus x square by factorial 2 plus x cube by factorial 3 plus dot dot dot, means it is infinite expansion of this one. We all know this series. We have used this series in various ways, in various times, in so many places, but this is the origin of this particular series through which we actually get the expansion or infinite expansion of exponential function with the help of power series. In the similar manner, power series can be applied for finding out the expansion of trigonometric functions, logarithmic functions, which will be discussed in the next class. But before concluding this class, I just want to mention another way of finding out the radius of convergence of a given power series. So it is alternate way actually, or sometimes some people are using this as the fundamental process, and the previous one what we have discussed is alternate. This is said as the radius of convergence will be r is equal to 1 by limit supremum an whole to modulus of an whole to the power 1 by n when this one mod of an whole to the power 1 by n is greater than 0 and it is equal to infinity when this part is equal to 0 and this is equal to 0 when this one is equal to infinity. So obviously someone can use this process for finding out the radius of convergence, and you can try this particular process for finding out the radius of convergence for the series. Suppose the first series 1 plus 2x plus 3x square plus 4x cube plus dot dot dot. Already we got the radius of convergence for this series is 1. We can use this particular format also to find out the radius of convergence, and you will see that the radius of convergence will be also 1 for this particular problem. And we are almost in the last part of our discussion for this topic. Before concluding, just 2 or 3 informations I want to share. The first one is that if a series converges for all values of x, then it is called everywhere convergent. Already we got one example where we got the radius of convergence is infinity. That means we are getting that particular series is everywhere convergent because that series was converging for all values of x. And one more information, if a power series converges for no values of x except x equal to 0. Already we got one example for this because we are already discussed all the variations related to this. Now we are actually making the conclusive statements from those examples, because we are not going to show all these direct proofs. We are actually making this from the examples, the verification, and after that some conclusions drawn from this. Then we say that the series is nowhere convergent. just the opposite of the first statement, that is the series converges for no values of x other than x is equal to 0. This is one more important and another important observation we can say. And final statement related to a final observation, I should say, that if a power series converges for some, here you get for all, here you get for no one, and here you are getting for some values of x, and diverges for other values of x, the totality of points x for which the series converges is called its region of convergence. Actually, we can write it in this form: the totality of points x for which the series converges is called its region of convergence. We have already understood what is radius of convergence. Now it is the region of convergence. So these are specifically three important observations what we have made from the last discussed three examples of radius of convergence for a given power series. So now we are going to mention that from which we have prepared this lecture, and also you have to find out these simple problems related to Taylor series and power series. And finally, I want to thank you all. Happy listening, happy learning.